Okay, so I didn't quite know the audience today, and that's why I'm going to decide some sort of like overview talk. It's actually a colloquium talk that I delivered a couple of weeks ago in Warwick. So if anybody of you attended the other talk, sorry, it will be the same, basically. So I'm going to mix and match all the results that I started to work on when I moved into the UK. So I moved in 2015, really. I started here as a fellow at Imperial College London, then I moved to UCL, and I'm back at Imperial College London. And during this kind of period, I started to interact with lots of colleagues from various universities here in the UK that are experts also in kinetic theory. So my classical education and analysis of PDEs, especially those in fluid mechanics, was influenced by elements of kinetic theory. And that's what I find particularly interesting now. I think it's a lot of fun. So there will be a lot of motivation at the beginning, and then I will try to introduce elements of analysis and numerical analysis, if time allows me, because I sometimes dwell on the details too much. So this is a list of my collaborators. I'm not going to be very specific about the papers, but all the papers are available on my webpage. So I'll start with some examples of models that I am considering in my work and the description of what they do. Well, first kind of first kind of family of models that I consider are models of swarms. And the swarm, I know it's quite a particular name, but by swarm, I'm understanding a big group of interacting individuals that are, so the individuals who are not just passive particles. I don't want to use the word not thinking particles, we don't know, but some individuals that actually can exchange information between each other using some sensory processing, or maybe they can sense each other through like fluid in which they are immersed. Or maybe they are parts of the same network, yeah, on Facebook or another social platform. So fish is just an example here, and we shouldn't focus on that. But the models that I work with are something that are called hydrodynamic models. And this is the so-called macroscopic scale type of modeling. It's presented here on the right-hand side. But of course, these models are not taken out of the blue. They can be derived from the microscopic scale models. And microscopic scale models, so the systems of ordinary differential equations that describe precise position and precise velocity of each of the individuals in the crowd, swarm, or shoal of fish. This is very precise. But when the number of individuals goes to infinity almost, we cannot really handle this sort of precision in the description. And nevertheless, it's very helpful to start from this level because we precisely can describe what sort of interaction do we want to see in our model later on. So I'm going to, I focus on two types of interactions in my research. First is the so-called attraction-repulsion force. So it tells you that, the force here, the right-hand side, is described by some potential K, that tells you what is the strength of the interaction between individual J and individual I. Yeah, you sum up over J is different than I. They don't have to be symmetric a priori, the interactions. So this kernel doesn't have to depend on the distance on me. It can, think about Facebook, right? And the fact that Barack Obama influences what I think doesn't necessarily mean that I influence Barack Obama, no matter how hard I try. So this is the sort of interaction that we would like to include as well. Second type of interaction is the alignment. So the first interaction was restricted to the exchange of information between positions. And here we say something about velocities. So there's some sort of kernel. It also depends on not distance, but the mutual positions of the individuals. But this kernel tells you how the velocities get aligned with each other. So when you, for example, what can happen? Yeah, these are two actually mechanisms that help the individuals to avoid collisions between each other. So this attraction repulsion force basically acts like a spring. So it stops the individuals when they are too close to each other. It's an example, of course, we can go more general. And alignment tells you that if they are sufficiently close to each other, they would probably travel in the same direction. So that's how you see this beautiful patterns of keys of birds in the sky, or fish like that. And now this form of non-local interactions can be actually inherited if you perform the really rigorous derivation of the hydrodynamic models. I'm not going to say how to do it right now, but there are great people behind this kind of results. So, for example, recent Fields medalist Alessio Figali has achievements in this part of the field. So he derives this sort of hydrodynamic models under various ansatz for the pressure. So more about it later on the slides. But what I want to say is that when we perform this kind of coarse graining or mean field limit or whatever you wish to obtain the hydrodynamic model, so system of PDEs, we end up with something that has a fluid-like structure of the equations. So there's conservation of mass and conservation of the momentum with all the forces on the right-hand side. But now the forces, apart from like maybe some local interaction described by pressure-like function, they also have this kind of non-local component here, which is denoted by F. So is there any question? Okay, then I'll follow. Please feel free to stop me whenever you feel like it. All right, so why it is interesting for me and why it was not like difficult for me to, well, not difficult, why it was, I felt like I can do something in this field, because those models, as you saw, they are not far away from famous fluid equations like compressible Euler systems or compressible Navier-Stokes systems. And in Poland and in Czech Republic, when I was growing up, where I was growing up as a researcher, we have lots of experts working in that field. So, but in fact, surprisingly, these models, although they have similar structure, so the conservation of quantities, there are like some crucial differences which cause problems. And hey, we like problems, we like solving problems, so that's great. But they also may actually provide some solutions, and that's what I'm focusing on. So if you plug in, again, the form of the force, attraction, repulsion, and alignment force to the macroscopic model that I presented in the previous slide, it's all written in one-dimensional case here. And you will see the following terms. Yeah? So there is local interactions in pressure, and for hydrodynamic models of interacting agents, this term, the local interactions, they usually are described by explicitly by some function of the density, but it's either linear or there is no interaction at all. So something that we call monokinetic ansatz. I'm not going to explain precisely how those two are taken or justified, but in this group of broad models, we see these two forms of pressure. And I'm not sure how much you know about fluids, but if you look at compressible Navier-Stokes equations or Euler equations, barotropic flows or isoentropy flows, this function would be something like rho to power gamma, where gamma is adiabatic exponent and it's strictly larger than 1. And there are some benefits for fluids coming from this form of pressure, which is of course going to be violated here. So the rough idea is that the information that we are able to obtain from the system about the density, just a priori, is lost basically because there is no nice growth of this function. So that's the first warning for us. Yeah. Second interesting thing is that although we don't have this kind of pressure that is typical for fluids, we have sort of term, which is now attraction repulsion term, that has similar structure. It's a gradient of something, right? Now think about plugging in front instead of K delta. I know we are not physicists here, but for the moment, let's say I'm gonna go back. we plug in delta here, so you actually get something like a rho gradient of rho right here. So it looks like, well, for delta, it will be very localized interaction, but we want to smear delta a bit. So the question, the interesting question for me was, can we say something about the system in a situation when the classical pressure for fluids is replaced by this non-local or smeared pressure, if you wish? So these are the important questions. Question number one, right? Question number two is related to the alignment force. So what I did, I presented here as a last ingredient two typical, or like maybe two extremal cases. So when the alignment potential or the kernel is equal to 1, the alignment force reduces to sort of friction. So this is just a friction term on the right-hand side. But if it becomes very singular, you end up with sort of fractional Laplacian in these equations, or even classical Laplacian, but it's modulated. This kind of dissipative effect that you have from alignment is modulated always by the presence of individuals. So when density is equal to 0, when there are no individuals around, they don't communicate like that, and this term becomes 0. So we have sort of degenerate dissipation. If you wish to use terms from fluids, is degenerate viscosity if the alignment is singular, or just a friction. So you end up with something like degenerate Navier-Stokes system with non-local pressure, or degenerate Euler system with non-local pressure. And the question is how much of the information from fluids you can prove for the system, or maybe you can prove something more. Maybe the nature that is behind these models actually gives you some better, nice properties. So we are in the fluid regime, but not exactly. Second group of projects that I wanted to explain to you are models of traffic. So the hydrodynamic equations, so partial differential equations that appear also in modeling of hydrodynamic processes, surprisingly can be applied also to describe the interactions between the drivers or pedestrians. Yeah, so this is more like general traffic modeling. And this is the picture that I did by myself. My son is very proud when I draw the cars. What I wanted to explain here is that those models, hydrodynamic models, are again derived from sort of macroscopic description, but the macroscopic description right now is different. So for the moment, I'm focusing on one lane traffic models for this slide. And in one lane traffic model, so in case when there is just one road and the cars follow each other, it's very easy to understand what the underlying mechanism would be. There is something that we call follow the leader approach to modeling of the traffic. And it means basically that the velocity of agent I is adjusted based on the information that the agent gets only from the car ahead of him or her. Okay. So, and there is some kind of course, communication weight that depends on the distance from the cars. The parameter gamma here is not accidental. When you derive the macroscopic model, again, this is on the right-hand side, and the parameter gamma appears in what we call cost function P of rho, which really plays a role similar to the pressure in fluids. So again, let's look at the hydrodynamic model that we obtain in the limit when number of individuals goes to infinity. So again, it's two conservation laws, very similar to the previous one. We have conservation of mass, have conservation of momentum, but now the momentum is not related to the actual velocity u, like on previous slide. It's related to velocity w. So W is some sort of desired velocity, and the actual velocity U is always less than W by a factor P of rho, which tells us what the cost or offset of velocity would be. So what is the cost of moving in ahead with velocity? Yeah, and this cost, of course, should depend on the congestion, right? If the congestion is high, we should probably slow down. We should probably even, stop at some point in these models. So that's something that is called Orozco model. It was derived, it was proposed as, I think in one of the papers that has very funny name, like what was it? Well, I don't have the precise reference right now, but some reincarnation of second order model of traffic, because they were long forgotten before Orozco really proposed this change, the transport of the velocity. And the derivation from micro to macro was performed a couple of years later, but it's still quite recent result from 2002. So now, just in case you thought the drawings cannot get any worse, there is another one. Now let's move to multidimensional world. Yeah. So if we have, for example, 2-lane road, who the leader should be in model like that? If I'm sitting here and I want to overtake, should I only look at this car ahead of me? No, I should also look at the car and the vehicle next to me. Or maybe, I don't know if you do it, but I really don't like when I'm on the highway and somebody is speeding behind me and is approaching me very close from the back. It definitely influences my decisions about how to behave on the road. So you see that in the multidimensional world, it's not that I'm going to add one more equation for another coordinate of my velocity and I'm done. It's much more complex. So if you want to use this sort of idea of Orozco, that the velocity, the desired velocity should be conserved, that's fine. But I think it's a very interesting problem to find actually the microscopic model that this two-dimensional Orozco kind of system can be linked to. Yeah. Moreover, if you think of one-dimensional case, there was no discrepancy or incompatibility of dimensions between the cost function and the velocity. So if you now want to move to the multidimensional world, you need to compare two vectors, two velocity vectors, with something that is also of the dimension of the vector. And P of rho was just a scalar. You remember it was rho to power gamma, right? So this is not good. This is not a solution. So we have to really carefully think what the model should be. The derivation is open, and the properties, of course, I study the properties of such models. Okay, so finally, I'm going to talk about the third group of the problems that I consider in my research. And it's more like hands-on modeling of what we expect to happen in crowds. So let me recall compressible and incompressible Navier-Stokes or Euler equations quickly. So the compressible system consists of continuity equation and momentum equation. Whether or not you are in the viscous regime, you add or subtract the stress tensor, but the equations look like that. For and the unknowns here are density and velocity. If you now consider incompressible Navier-Stokes or Euler equations, the continuity equation changes into divergence u equal to 0 condition. And we have another unknown. So the density is known right now, something like rho star is given. But the new unknown pi is just a Lagrangian multiplier associated with this incompressibility constraint for the velocity. Okay, so you need to make sure that you project on the right space when you want to do the weak formulation of this equation. So I wouldn't necessarily call it the pressure, but something that some additional unknown in the system. And now, if you think about like just trying to use fluid language to describe big groups of people without really thinking on how the interactions should be, you would like to maybe look at the crowd and see that there are some regions of the crowd where people are very close to each other and probably they cannot compress anymore, right? But there are also these regions here where there is lots of space and they can still approach closer to each other, right? So what we want to do is to combine the two systems that I described before, so compressible and incompressible equations, in such a way that we don't determine precisely what happens with the interface. The interface can be very topologically complex object. We only want to say that the systems switch from one to another, compressible to incompressible, when some constraint on the density is reached. Yeah, it makes sense, right? We have our physical sizes, which are translated to the density, right? 1 over volume. And assume for the moment that all these physical sizes are the same, then this constraint instead of rho star would be 1. Yeah. And this two-phase system tells you that there is, that you have some sort of switching between compressible and incompressible regime if rho hits this critical value rho star. So let us look at the switching relation. If rho is equal to rho star, this condition is satisfied automatically, right? Rho is equal to rho star, some given value. So it is given, you plug it in here, you obtain divergence-free condition. Yeah, rho star is a constant at the moment. So you obtain divergence-free condition and you go back one line up, you know that now, okay, pi can be whatever, larger or equal than 0, and you end up with incompressible Euler equation in this case. Now, if on the other hand, rho is less than rho star, strictly less than rho star, then this condition tells you that pi has to disappear. So this additional unknown pi has to be equal to 0, and you end up with something like compressible Euler system. Yeah. So that's a way to consider two systems in the same system with having this kind of relationship, which we don't know even what it is, because pi's are unknown. Yeah, so it's like one extra equation in your system. You have 3 unknowns. So a big chunk of my work has been devoted to this sort of systems, but I was not the first person interested in these systems. Maybe one of the first few people interested in the systems in the context of pedestrians modeling. But sorry, I will put the headphones because my neighbor is already in his office and he is having some kind of touch, which is a bit distractive, at least for me. Okay, so the system, what we call pressureless Euler system with the constraint like that, has been already considered in the literature, and people are trying to approximate solutions to such system, or at least explain how the system can be derived in many contexts, not only pedestrians. I think I have a slide on that coming up. Just the interesting thing is that well, my approach is a bit different. Like I come from this fluid community, so I focus immediately on solutions, on weak solutions. But people who came up with this sort of systems, they see them as the limit of what we call sticky blocks approximation. So they were observing how blocks of describing some objects of constant mass, how the behavior of macroscopic behavior of a model would be if we assume that when the blocks meet, they stick together and they travel together with the same velocity in one direction. So that's something that you obtain as a macroscopic limit. And there is a vast literature for systems like that, especially in one-dimensional setting. In multi-dimensional setting, it's still not very much available. Now, similar systems appear also in the study of traffic jams. So you remember when I told you that there is a problem with the two-lane modeling of traffic jams. So now one of the possibilities would be again to use the compressible incompressible system with variable density rho star. So if rho star depends on x, this x could model the width of your road. and that model, two-phase model, has been used in this context. Another interesting application, but is modeling of the flow through pipes. So now our density is not density of the fluid. The height of the fluid plays the role of the density, and when the height of when the fluid touches the upper part of your pipe, in place of our pressure, in the fluid models, there appears like a gradient of some function here, some additional forcing coming from the ceiling of the pipe, and that's the interpretation of our pipe from the previous slide. So, so that's the application of much more complex situation when rho star depends on X. The limit system is a bit different. It's not just incompressible Navier-Stokes, but you can get the idea of what it would be. Now, the interesting thing and the real something I really wanted to understand, because my motivation came from modeling the crowds, is what if this rho star, if this constraint is not a constant, it is not something that depends only on space, but it's actually something that depends on time. Yeah. So if we think about rho star as a preference of the pedestrians, right, as their individual preferences, like how close we allow people to approach each other, right? I don't feel comfortable in London buses, but some other people do feel comfortable, yeah, when it's like total squeeze. So it's an individual thing that is probably prescribed initially, and one of like the biggest contributions of Pierre Degonde, who was my collaborator on this project, was to actually come up with the simplest equation for this rho star that makes perfect sense. So I was a bit stuck on this problem because I always thought, okay, let's take rho star, which is very general function of time and space, and let's try to say something for this model, for this system. And he told me, no, Ewelina, it cannot be like arbitrary. It should be traveling together with the flow, right? Our preferences evolve. Let's fix that they are given initially and they move together with us. Okay, we'll see what will happen. And it turned out that this was a brilliant idea, and it helped us to do like analysis, rigorous analysis, and then numerical simulations for those systems, confirming that, well, first of all, that they can be approximated by one-phase flows. And then second of all, that they are really giving us interesting sort of patterns in lots of physical situations in which we want to use these macroscopic models, like evacuation from the room, for example. All right, just to explain maybe what is going on, if the density rho star, if the restriction for the density depends on time and space, I have prepared this very simple simulation on MATLAB. So what you'll see here is the density. So the blue line is the density, the red line is the rho star, so the thing that will evolve with the transport equation, basically. You see initial velocity here, which is a positive, so it's one-dimensional torus, yeah? Velocity is positive here in the middle, so it means that it will move in that direction, and negative here, so we will have some sort of stretching here and pushing the fluid or the individuals toward each other here. And finally, what you should focus on, really, it's going to be quick, that's why I'm saying what you're going to see and what you should see, is this kind of pressure. So this singular, well, not singular, but this extra unknown that appears only when these two lines meet with each other. Okay, so the simulations are not done for the two-phase flow. They are actually done for the purely compressible system that we used as an approximation of the two-phase flow. And we are able to prove rigorously that one system converges to another with some parameter that I'm going to explain later on. So let's see what's happening. Immediately, we see that the density was pushed towards its limits
you see that there is a relaxation of this kind of crazy oscillations of rho star, and there is some sort of equilibration in the system. And that the pressure, of course, appears only in the contact areas when the density really touches the rho star, the limiting value rho star. So what are the fundamental problems to solve here in this theory? First of all, for me particularly, I'm an analyst. I'm always interested in the question whether the systems, PDEs, are well posed. Yeah, how do we start? Whether there is some framework for existence of solutions. Do solutions exist? What sort of solutions? If I want to talk about large data, if I want to talk about behavior for very large times, probably, as we know, for systems of conservation laws, classical solutions might be not the best way to go. Not even the entropy solutions might be the good way to go. So I subsequently was more and more relaxing definition of my solutions from weak to measured valid solutions. Also, when you add some elements of randomness, you may want to talk about martingale solutions or statistical solutions, all sorts of solutions that we cannot like really take and show to our students because they are like scared basically. And then once you have existence of those solutions, of course, this is not the end of the story. You really need to say something, why those solutions are useful, right? You have to justify why what you're doing has a meaning and why it is needed. So how weak can we go with the definition of the solution for the solution to still make sense? And what does it mean for the solution to still make sense? So quantifying this, yeah, finding out what are the conditions necessary for the solutions to have some sort of uniqueness. So maybe conditional uniqueness of the solution are the questions I'm trying to answer for those three types of models. And now, once this is addressed, of course, the interesting questions is stability of solutions. And actually, when you drop the name stability of solutions to different groups of people, they can have different meaning. So for me, stability of solutions means what is the long time asymptotic of the solution? And of course, this is interesting also for the applications, because we kind of want to make sure that these macroscopic models, they describe some sort of consensus in the system, yeah, or maybe formation of some patterns that we see in the microscopic systems. Yeah, we want to make sure that the macroscopic models are calibrated well to be useful for us, yeah, that's what I'm trying to prove rigorously, that some profiles are stable for the solutions. So you can sometimes it's not possible to do it for arbitrary data, so we also do perturbations, perturbation theory around some profiles that we expect to happen there. But stability also means for me stability of the system as it is, or maybe if I want to disregard certain features of the system and focus on, I don't know, what happens in the small compressibility regime, or when the flow becomes stratified, or if there is some forcing that is dominating my flow, yeah, then it's then you actually want to check what is the change in your system if you send some parameters to zero, and that's what we call by singular limits of the system. So you want to go, like you want to get your solution, original solution, and see what the solution does if the system changes, whether there is stability of solution if the system changes, yeah? So that's another field. And finally, I'm interested in stability of numerical schemes, of course. And the third group of problems that I investigate or want to investigate. So by the way, this is all covered in the fellowship that I'm now that I have received recently. It's a 5-year project, and I'm hiring postdocs and PhD students. So if you know anybody interested in this field, please send them to my webpage or please ask them to contact me. And the final stage of this project, so something that I'm not going to touch on today, is what happens if, apart from interactions between the agents, we actually introduce a lot more physics into the systems. So for example, for the models of spermoids, yeah, for the micro swimmers, it is really important to include viscosity of the fluid around around the interacting objects, right? The same for models of polymers, the same for models of bacteria, the same for models of all living organisms in our blood. It's really important to know what is the interaction mechanism, and if it is like binary interaction or if it is continuous interaction through the medium. And the question is, of course, if you try to couple the models, get more like complex, maybe mixture models, or maybe multi-phase models, or just some bubbling regime models. Does it help you with like improving a bit the regularity? So you can think of these models as some kind of transfer information between kinetic models and the fluid models, right? And I already spent a lot of time explaining you how many benefits we have in fluid models, and that we would like to maybe prove something analogous for kinetic, for the hydrodynamic models of interacting agents. So maybe just by this coupling, we can actually get some more information about the kinetic models. So these are the sort of questions I would like to address, I would say, like in 2 years. So I already spent a major part of my talk discussing the problems, and there are many, many more. Now let me give you some examples of solutions. So for first model, for the model of crowd, what we are able to say is we are able to deliver very precise information in one-dimensional setting. So alignment is disregarded here, but it is not a big issue. It has been actually done. It's actually helping you if you introduce alignment. But what we considered together with young Pil Choi from Korea and Jose Carrillo from Oxford is the Euler type of system, pressureless Euler type of system with friction instead of alignment. So it's a very basic system, and non-local interaction of very precise form. So there is like a linear repulsion and quadratic attraction term. Yeah. And we can prove for such system equipped with initial data that are smooth and some additional information about initial mass and initial momentum, that the system has a smooth solution basically as long as the solution exists. And what is wonderful about this result is that you start from system of non-local PDEs, but just by very simple transformation. I like to talk about this result because it's very simple, and I can like ask students to do all the computations, and it's really fun to see that in PDEs you can actually end up with an ODE. So if you write system on characteristics, first of all, your moving domain, yeah, so whatever was happening, well, on the moving domain becomes fixed. That's one thing. And then if you look closely into the structure of your interaction, the potential K, well, first of all, it was symmetric, right? But then you'll see that the derivative of this potential is antisymmetric. And if you differentiate this momentum equation written on the characteristics, use the properties of the right-hand side, you will end up with ODE. And voila. So we have ODE, we can solve it exactly, explicitly. And now the only hard part, well, not hard, it was hard to come up with this transformation, but the only tricky thing is try to identify the condition that tells you what does it mean to have a blow up of the solution in such case. Yeah, so the result was delivered in 2016. We have these precise conditions for blow up of solution. Blow up of solution means for us blow up in the density, so an infinity bound of the density is unbounded anymore. And what we also showed is that if the data are in a safe regime where the blow up doesn't happen, we have convergence to something that is called consensus. The solution converges to characteristic function basically of the interval, which is propagated for us with velocity 0 because we have this kind of damping, the friction. But as I said, for other forms of alignment, this can be something else. So this is a precise result in form of precise assumptions on the initial mass, initial momentum. We know the speed of convergence of the density to the profile. And what I wanted to tell you is that although we know this, it's not the end of the story. And sometimes being very ignorant, as I am when I'm doing my numerical simulations, really gives you like lots of ideas of what to do in the future. So let me talk a bit about this blow up, and I will explain you why it is interesting to not stop where we stopped. So what you see here on the picture on the left is a density profile. So initial density profile is something nice. It is all in the Lagrangian coordinates. So the characteristic coordinates. So the interval is fixed. Initial density is like that. Initial velocity is just something of constant gradient. So that's fine. It's not very steep. And you'll see that when time goes to infinity, here it's very short, the density stabilizes into this characteristic function of the interval, which is the width of this interval is prescribed by the initial mass, of course. But if your, sorry, I need to go back. If your initial velocity is too steep at some point, like if the gradient is too big, it is related to the density condition. Then at some point you see blow up of the density like that. Inside the domain, you have just a formation of the peak. Yeah, and that's what our result tells us. Either we have blow in time solution or we have blow up in finite time. Yeah, but an interesting thing happens if you run your simulations past this blow up time, which I did. You'll see that this singularity formation is just temporary. Then the singularity gets dumped, and for larger times, longer times, you still see formation of consensus. So I would love to have a postdoc who would be able to explain why this happens and yeah, maybe work in this direction as well. I think I still have like 2 minutes, or should I stop sooner
yes,
for questions?
2 minutes.
2 minutes, okay. So this result has been generalized to a multi-dimensional setting, and it's much more technically involved result. I don't want to say that there is much of interpretation in terms of crowd dynamics or anything like that. It's just one of the first results that was like combining the non-local effect from the attraction repulsion sort of interaction and the local pressure. And it's very interesting to see what is the interplay between those two terms. And I think it's also opening some door to further understanding of whether the purely local interactions can be completely replaced by the non-local interactions. There is another paper that we produced together with Kario Wróblewska-Kamińska from Warsaw, following this result, when we were able actually to show, so this is sort of a viscous system, yeah, there is a stress tensor. But in 1D, we were able to show that there is a link between this system, so the viscous system, and viscid limit, the system that I was able to characterize precisely because it was an ODE. And this kind of approach, this kind of singular limit that we considered, really helps us to maybe get some confidence that there is some notion of the solution past the blow-up time. Well, yeah, and this would be great to investigate a bit further. Right, so I would normally I would like to talk about solutions to problem number 2 and problem number 3, but I'm not going to do it today. Anyway, it's kind of heavy analysis. It's lot of like very refined definitions maybe and theorems to prove. What I would like to conclude with is to say that these macroscopic models, the two-phase models, have been applied by us to model evacuation scenario from the room. So the two-phase model, we are able to prove that it can be approximated by the compressible, purely compressible model, and that the results. So what you can see here is a simulation of a quadratic room. So you have, well, this is a space filled by some pedestrians, and you open the door for them. So all of them want to go through this door. And there's no time for running the simulation really, but what you see here is like basically density distribution of this pedestrians, and you see some sort of stop and go waves that were previously known only for microscopic models. Yeah, so some sort of clogging of the individual's coastal door. It's not clear why this should happen for fluid models, right? It wouldn't have happened if we didn't have this kind of two-phase structure. So I'm really optimistic about these models, and I think they are a great source of problems and great source of great potential for applications. So let me stop by that, and thank you very much for your attention today.